everybody. This is Dr. Collins again with another video. So today we are going to be talking about statistical significance, but it's a little bit different than the last video. In the last video, we focused more on the logic behind a p-value, right? What is a p-value? What is statistical significance? And it's all about that idea of uncertainty, right? So I want to continue with that by talking from a little bit more of a mathematical approach about statistical significance and, by extension, of course, statistical inference. Okay, so there's one of my favorite cartoons. I think I've shown that to you before. All right, now we're going to start this agenda by revisiting the central limit theorem, which is that thing we talked about before the break relating to probability that is really important. It's really the foundation for statistical inference. And then we'll talk a little bit about the role of the null hypothesis and what exactly we are testing, right? And there you can see that fun little figure that shows, central limit theorem really is the thing that brings us p-values, right? That's where babies come from. So to revisit the central limit theorem very briefly, right? If you think about any variable out there, something like height, weight, IQ scores, country's democracy, right? Things like that. It can be any distribution. It could be bimodal, that is, it has two bumps. It could be skewed heavily one way or the other, like income, of course, would be. It could be any distribution out there. Now, if we were to take lots and lots of samples of that variable and test that variable, right? So let's say we took 10,000 random samples of some population of interest and we tested that value. And we calculate some statistic from those samples, right? Remember, a statistic is an estimate of a parameter. Statistic is for samples, parameters are for populations. All right, so if we calculate some statistic from those samples, the distribution of that statistic from each of those samples, that's called our sampling distribution, that's going to be normal. That's the central limit theorem. Right? So again, we never actually do this. Right? So again, a brief hypothetical would be, let's say I'm interested in Siena students, how they are responding to COVID-19, right? How secure they feel in their coursework in the wake of COVID-19 and the adjustments we've had to make. Okay, so let's say I do that on a 1 to 5 scale, right? 1 being completely unprepared, completely freaking out, 5 being completely comfortable, no problems at all. All right, that's probably going to be a little bit skewed, probably towards the lower end of that scale, right? Something more like a 1 or a 2 or a 3 rather than a 5. Now, if I took, let's say, 10,000 random samples of 100 Siena students, okay, and I asked them that question, the mean from each of those samples, right, you could then plot the distribution of those things. Okay, and if you plot all 10,000 of those sample means, you'd get a normally distributed variable, a normally distributed sampling distribution, right? And the mean of that sampling distribution would be the population mean, right? We did this with coin tosses, right? You could get one really aberrant coin toss, but the distribution of 10,000 trials of 100 coin tosses converges on 50%, which is the true population. Okay, that's a sampling distribution. This works for whatever test statistic you're using. You could be looking at means, which we'll work on a little bit. You could be looking at correlation coefficients, which we've already talked about. You could be talking about z-scores, which we'll get into late next week, t-scores, which is after that, regression coefficients, which are after that, whatever you want to look at, right? If you conducted 10,000 samples and you gathered all that information, right, you would get a normal distribution of those test statistics from each sample. So what? Why do we care about this? Well, if you remember, there are important characteristics of normal distributions. That is, we know how much of the data, that is, how many observations, or in this case, samples, right? The sample means are each observation in a sampling distribution. We know how many of those are going to fall within 1 standard deviation, within 2 standard deviations, et cetera, of the distribution's mean. which should be the population mean, right? So here's that figure again that we've talked about before. Now this figure shows us, right, that within one standard deviation of the mean of a normal distribution, that contains 68% of the observations. 95% fall within two standard deviations. 99.7 fall within three standard deviations. Okay, so now that we know that, if we were to assume, now this is important, if we were to assume the population value is a certain number, right? We don't know the true population value. Yeah, if we took 10,000 samples, we'd get a sampling distribution whose mean converges on the true population mean. But we never do that. That's impractical. So if we were to assume, treat as a given the true population value, we can estimate how likely it is we'll obtain the sample we obtained. Okay, so let's think about that. Let's assume the true value is 9 and the standard deviation of this variable is 2. Okay, in the population. Now, we conduct our sample. We look for whatever we're looking for, say it's mean of something or another. We obtain a value of 5. How likely are we to obtain this with a true mean of 9? Well, we know that the mean is 9 of the true mean. We assume that to be the case. Standard deviation is 2. 5 is 4 away from that mean. So it's 2 standard deviations away. That's where 2.5% of data fall. Right? If you go back, right? If you were to go back and look at this figure, right? You will see that 2.5% of the data fall 2 or more standard deviations away from the mean, below the mean. Okay, so that's really important to consider. Now, what we just did is calculate a p-value. There's a 2.5% chance we'd get this if the mean were really 9. Okay, why? Well, because 97.5% of the observations are going to be greater than that, greater than 5, if the true value is 9 and the standard deviation is 2. We just calculated a p-value. That's it. It's the chance we'd observe this sample, 5, if the true population value were 9. That's it. Okay? So, what do we typically assume to be the true value? Ignore that little thing down here. That shouldn't have been there. That's fine. We'll ignore it for now. We typically assume the null is true. Right? As I've mentioned many, many times before, one of the first things we do is we assert a null hypothesis, and we assume it to be true. Okay? That the true relationship between these two variables is 0. There's no relationship. Right? So if we're testing a correlation, the null hypothesis would be we assert that there is no correlation, exactly 0. Okay? Now, in our hypothetical sampling distribution, the mean of our test statistic, whether it's correlation coefficient, regression coefficient, whatever, is assumed to be 0. From there, we take the data that we have and we calculate our test statistic within our sample. We assume the true value is 0. We calculate what our sample tells us. We compare this value, this observed sample test statistic value, to the assumed true value of 0, the null. And we figure out how many standard deviations away from 0 are we. That's it. This tells us how likely we'd be to draw this sample if the true population value is 0. That's a p-value, right? It's the chance of committing that type 1 error that you reject the null even though it's true. Okay, so that's the chance. So let's go back to our prior example, 2.5%, p equals 0.025, right? We would have a 2.5% chance of rejecting that value of 9 that we assume to be true, even though it's true. It's unlikely we would get a 5 if the true value is 9, is the point. That's what's going on here, right? We see how likely it is to get a sample that far away from the true population value we've assumed to be 0. That's all a p-value is. Okay, so again, right, we assert that this mu here, the true population value, whatever test statistic we want, is going to be 0. We calculate our test statistic in our sample. Let's say it's 1 standard deviation above 0. If that's the case, there's a pretty good chance that we get that, right? 100% of the data fall below this curve, all right? 68% fall within 1. That means that out here on this tail is 100 minus 68, which is 32, divided by 2 because it's symmetrical, 16%. There's a 16% chance that we would get an observation 1 standard deviation above the mean, above that hypothetical mean of 0. Okay, that's a pretty good chance. 16% is a pretty good chance. All right, ends up being something like 1 in 8. That's pretty good. All right, so we don't want to reject the null in that case. If, however, there were a 2.5% chance, right, it's 2 or more standard deviations above the mean, then yeah, we could feel pretty good rejecting the null. So what are we testing here? We're actually just testing whether or not our observed sample fits with that hypothetical sampling distribution where the null is true. That's it. We are not directly testing our alternative hypothesis. We're not. So a quick caveat here. In a sampling distribution, we don't actually use the observed standard deviation to calculate p. Okay? There's a good reason for this. All right? The observed standard deviation is for that variable. But what we're trying to look at is that sampling distribution, not the distribution of that variable. Right? The sampling distribution is going to be, again, if we took 10,000 samples and plotted whatever test statistic for each one of those samples, that's our sampling distribution. It's going to be normal. Okay? The standard deviation of that isn't the same thing as the standard deviation of the original variable. Instead, we use the standard deviation of a sampling distribution, which is called the standard error. Okay, we're going to get a lot more into that next week. Okay, so that's an important caveat. We're not actually using, if you look at, say, the mean feeling thermometer towards Bill Clinton and the standard deviation, the mean feeling thermometer might be, 55. Standard deviation of that might be, 10. Okay, if that's the case, right, if we took another 10,000 samples and asked that question, the standard error would not be 10. Okay, now we'll get into the specifics of all of this later on, but there is a bit of a caveat there, right? The standard deviation of a sampling distribution, that's what we're really interested in. That's called the standard error. Okay, we will get into that, I promise. So, quick review. Central limit theorem tells us that a distribution of sample statistics from repeated samples will be normally distributed. Okay, that's not new. We assume the null is true. That is, we assume that the sampling distribution has a mean of 0. From that, we calculate our test statistic, whether it's correlation coefficient, regression coefficient, whatever. And we calculate its distance from the null, which is the assumed hypothetical mean of that sampling distribution. This is how we get our p-values. Now, previewing what's to come, I've talked about this already. The next set of lectures, which you're going to have to do for Tuesday, that's March 31st, I believe, right? You're going to have to do test statistics, and we'll have to do some confidence intervals. Okay, so we'll talk about that for next Tuesday's class. But for now, hopefully you have a better understanding of what p-values are, where they come from, what they mean. Okay, whether this video helped you more or the previous video helps you more, doesn't matter to me. I just want you to understand kind of what a p-value is. All right, I will be in touch with you all later. Thanks.